Okay, so just before the break, we were seeing about the shooting method, right? Shooting method and finite difference method in order to solve these boundary value problems, right? So the idea behind the shooting method is you will transform the boundary value problem into a set of initial value problem, and then use any kind of method you have you want to use and march ahead. In the finite difference method, so wherever you are seeing the derivative, you can approximate it via a central difference scheme or forward finite difference or backward, up to you. So once you do that, you will end up with a set of equations which you will solve it. You will have required number of unknowns and number of equations equal to number of unknowns. You will solve it as a simultaneous set of equations and get those unknown values. So all these two methods are involved like transforming the boundary value problem into a set of IVP or a set of simultaneous equations. So we will look into them one by one. So as I told you, like why we need the boundary value problem and why the methods, numerical methods devised for initial value problems will not work out. Okay. For that, we will have an analogy of that. So just before that, I told you, suppose this is the ground, just a fun example, and say this is your target. Okay, and say this is your tanker. Okay, all right. So now the tanker will be firing like, missiles or something like that. So your idea will be what? What will be your idea? So this is your x equals to a, where you are starting, and this is your x equals to b, where your solution is ending, right? So now, suppose you aim to the you are aiming. So you are aiming here, right? You are aiming here to the solution. So, but maybe the aim you did is just falling here. We don't know, right? So either like when you fire the what do you call it, missile, okay? Happen that he is going very far off the target, okay? So both of the cases are not useful to us. Both of the cases are not. So therefore, like maybe you target in a very nice way such that it is hitting here. So this is our required equation, right? This is our required trajectory. So this is our required trajectory, so that you start from x equals to a, you fire at this angle at this much speed so that it will hit the target, right? So this is the motivation behind the shooting method. First, we will see that you aim and then you shoot. Okay, that's the idea of the shooting method. Right. So the name has been derived from this. So let us start with this. Suppose you have a boundary value problem of x, fx, then its derivative f dash x, then it will be like a double derivative of f with respect to x. Okay. As the boundary value problem, what I need to set? I need to set the value at two boundaries. That is, what is f of a? Yes. So suppose like subscript a, and say f of b, which is the next boundary, is f of. So this is a boundary value problem. Now our aim is to solve this using the shooting method. So what's the first step? So the first step will be start by guessing. Okay, start by guessing what is f prime of a. Okay, say you are guessing. So you are guessing this. Say f prime of a is alpha. Okay. Now if you know f a equals to f subscript a, and f prime of a equals to alpha. Now it's like an initial value problem, right? Then you can march ahead with any of the method you know, right? Then when you reach x equals to b, I forgot to write this. So on till you reach b, okay? Then as well, okay? So that's the idea. So this is the step one. Guess the derivative at the initial point, f prime of a. Say it to be alpha, okay? So now we have an IVP. Great. What's the next step? What is the next step? So next step will be to use the RK4 method to integrate to the boundary. It's okay for you? Now use RK4 method. RK4 method. Why we can use RK4 method? Because now it is an IVP here. You can use RK4 method. After using the RK4 method, our aim is to go till x equals to b. Okay. Then you're using Ranjit, the use of Ranjikuta method, right? So that is like you might get some value of f. Yeah. Okay. But I want your attention to this matter that f of b is already given to be f subscript b. If your guess is right, if your starting guess f prime of a equals to alpha correct, then you will hit f of beta equals to f of b. Yes. If your guess f prime of a equals to alpha is not correct, okay, let me write. If your guess is correct, then what will happen? Fb equals to f of beta, right? If your starting guess alpha is correct, then f of b equals to f of beta. Now, if it is incorrect, then f of b is not equal to f of beta. So this is the third step actually, to actually compare the values of f of beta and f of b, right? So if your initial guess is not, beta won't be equal to f of b. If your guess is good, f of beta will be b is equal to f of beta, then you are done. You don't have to do anything else. Now, if work to do, then you have work to do. What is your work then? What is your aim? Your aim will be this to be 0. So this is a, so your aim will be to achieve this equation. Make f of b and f of beta in such a way that you have f of b minus f of beta equals to 0. Okay. So this is an equation, and you can use it. Got the idea? So, just apply the shooting method to a very easy problem, not to any big equation. So our problem will be, we are going to launch a rocket. Okay. So we are going to launch a rocket. So launch a rocket. But we can specify some variables, right? So you can specify like y of t, because the position of the rocket varies with time. Okay, that's the altitude of the rocket it reached at time t. So y of t represent the altitude in meters. B altitude is altitude in meters. Okay. from the surface of the rocket at time t, right? Then you know the gravitational constant g is like 9. Is if we want to have the rocket at 50 meters off the ground after 5 seconds, okay, then what should be the velocity of the launch? Let me write it here. At the rocket, want to have the rocket at off the ground uh, after 5 seconds. So starting from 0 till 5, within 5 seconds, the rocket should be 50 meters above the ground. Then for this to achieve, what should be the velocity of launching? Any ideas? So you don't need, like it's a bit of physical problem to appreciate the method better. So you know the ODE, right? You know the ODE that d2y by dt2 equals to minus g. Yes? Acceleration d2y by dt2. And that's like just the gravitational constant minus g. Just acting in the downward direction, it's a vector kind of thing, hence it's pointing downwards. Just convention. And we have two boundary conditions, okay? Like y of 0 is 0. Y of 0 equals to 0. What is that? So the altitude of the rocket at time t equal to 0. At 5 seconds, it should be 50, as given in the problem. Yes? So then it is asking what is the velocity of the launch. Launch means at time t equals to 0. Yes? Velocity means the derivative of y. So it is asking us what is y. You can frame this question up, right? You can see how these are getting connected now. So, yeah. So, yes, after you solve it analytically, try to solve it analytically. Homework. So you will get y prime of 0, 34.5. Check it. Check it again. Okay, check it again. Okay, so we have done this. Now we will use the shooting method to understand this problem, and you solve it using Python. Okay, understand at least using Python. Second order ODE into a two set of first order ODEs. How? Pretty intuitive. To V, then 2 minus G. dy by dt, you are saying a variable v, that's a velocity. Then the velocity varying dv by dt, which is like just that you are saying as minus g. So this is like a set of two ODs. Okay. Write in a better way. Maybe I should write in a vector form because I will use this vector form in the Python. So what I will do, I will just declare one of the vector s of t as y and v, right? Then your ds by dt will be matrix multiplied by s of t. Oh, that is a zero component of y. So put a 0. Does dy by dt have a v component in it? Yes. It has. So put a 1 because it is getting multiplied by this V. Then what you have to do, check again. For the second equation, dv by dt equals to minus G. What you can do here? Same in the first row. Because when it is multiplying with a V, yes. Okay. So we will see this in Python how it is solved. Same problem we will take learning about this finite difference method as well. So let's see by the shooting method. So this is the same problem we are doing it here. All right. So as you can see again, I'm importing solve IVP, which we have discussed last class. So I want to remind you again, Gecko is one of your projects. Optimization library Gecko. Acts as a lambda function t comma s, right? So you can see it is the vector which I have just written now in the board as the first row. Yes. Can you recheck? Can you recheck? Then the next row, second row is 0 minus g by v. So 0 minus g is minus 9.8 by v. V is s of 1. I have written it here. Okay. And then we are multiplying with s. Okay. So you are defining here also like t span that is what's the time it will run up to till 5 seconds. 0 to 5, and we are using lane space 0 to 5 100 times. Okay. Split it within 100. Y naught is 0. At time t equal to 0, your position is 0. And yes, V naught is your guess here. V naught is your guess. Okay. Like you remember during the start of the shooting method, I took as the derivative alpha as the initial guess. If the initial guess is right, it will hit target. Okay. So let's see. I have taken 40. If it doesn't hit, we will check again. T eval. That's where we will integrate our ODE using solve IVP. So this is from the last class again. Solve IVP function. Solve IVP F, which you have defined above. Y naught and V naught you are specifying initial condition as argument. T you are specifying the array 0 to 5 of 10 steps. That's it. Your boundary value problem is being converted into value problem, which is the task of shooting method. Why it happened? Why we are confidently using IVP? And due to that initial guess, that boundary value problem got converted to an initial value problem. Okay. Now you can use your solve IVP method. We could have used, but we can directly call the library solve IVP. So you are plotting it. Let's look how it looks. So this is the output of this. Altitude I'm plotting on the y, time on the x-axis. So these are the value of y you are getting via shooting method. Okay. So you can see the star is actually your target. Star is actually the target. When I take 40, it is not hitting. When I take 40, it is not hitting. It should hit, this point should hit here. I think I have done, is it now? Okay. So instead of V naught equals to 40, we can now change it just to see the effect, right? Any suggestions? 30. 30, it is going downhill. Previously, it was going uphill. Now it is going downhill. So that should give you an intuition that it is somewhere lying in between 30 to 50. Now you have to use the bisection method and your ideology like it. So we can play around with it. Uh, Previously I took 40, is it? So 30 to 40. So what we can do is 35 now, the midpoint. Yes. So coming closer. Okay. So now you can, but not accurate enough, right? So now we had 30. Now we are having 35. What we can do? Take the midpoint. What is it? 32.5. Coming down. Okay. So slowly increase. Let's see. Yeah. So now you can see that just by using the root finding method, which I have used it manually, you can actually hit the target. Okay, so that's the usefulness of the shooting method. Any boundary value problem, how much complicated, you can solve it using the initial, by converting them to initial value problem, by guessing the derivative. Then you check if your derivative is correct or not. So therefore, in a boundary value problem, some might think in a boundary value problem, solve a boundary value problem, why we are calling solve IVP? Bit tricky, right? The main motivation is in a shooting method, you are converting the boundary value problem into an IVP. Therefore, you can use all the tools available to solve IVP. Right? So therefore, you can see that 34.5, if I set, then it actually hits the boundary, like actually hits the target. So therefore, you can easily see that now 34.5 is actually the correct answer. So you should launch your rocket at 34.5 meter per second square, so that after 5 seconds, it will reach 50-meter height. Get that idea now. Okay, so let's look at another method. We learned and had some fun. Now we look into some other method, okay? The next method, which is the finite difference. Finite difference method. As I told you already, it will take a boundary value problem and you will discretize the boundary value problem using some approximation. What kind of approximation? Finite difference approximation. So wherever by a central difference scheme, and you will have a set of equations. So the idea is converting the boundary value problem into a set of simultaneous equations and then solve it. Okay. So just a graphical viewpoint. So you can have this curve over here. Okay. You have starting point is equals to A. And your final point is so the idea is, since it's a finite difference scheme, the idea is like to divide the grid into fine steps, finer sizes. So that means point is x naught is A, this is like y naught. Another for some time step, like equidistant time step, say this is x1, x2, so on. Okay, till you reach here, say xn minus 1. For each of these points, correspondingly, you will have the points, right? Like similar for xn minus 1, you will have it here. Looks very far. Maybe I'll put it here. This is yn. This is your yn minus 1. This is your y1, y2, and so on like that. Yes, you are dividing that into very tiny pieces. Okay, that's the idea. So what kind of, so wherever you will see dy by dx, wherever you will see dy by dx is being given to you can use the central difference scheme. Yes, wherever you see d2y by dx2, yi plus 1 minus 2yi plus, it should be minus yi plus 1. Doesn't matter, but I want to go in a sequential way. Right? Yes. Correct, right? Yeah. There should be an S square. Okay. So wherever you see this derivatives in your question, and then solve it. Okay, using those equations. So these will replace your derivatives, and finally it will lead you to a n plus 1 linear algebraic equations. Okay, which you can simultaneously solve. So we will come to our rocketry problem again. Okay, the same problem. So we will solve it using the finite difference method. What you have, what you had is d2 d. Sorry for that. So d2y by dt2 equals to minus g. Yes, y of 0 equals to 0 and y at 5 time t equal to 5 seconds is 50. Now you solved it using the shooting method. The idea is, can you solve it using the finite difference method? And does it give the same answer? So what you can do, say I'm just giving this problem, say n equals to 10. So you have to divide 0 to 5 in 10. So that means h equals to the final b is 5, a is 0 divided by your number of steps, that is 10. That is like 0.5. So you will go from 0, 0.5, so on till 5. So using finite difference scheme, you already know y naught equals to 0. So can you establish the finite difference scheme? That's the question here. So pretty confident that you can do. How you can do? Replace the second order derivative with the central difference. How you will do it? Yi minus 1 minus 2yi plus yi plus 1 divided by h square. That I am taking it as this way. Is it correct? For now, you have n equals to 10. For different n values, you can generate the equations. Am I correct? So if you can transform this set of simultaneous linear algebraic equations, and you can put it in form of a matrix, and you can solve that matrix, right? So how you can do that? See, we have to capture the coefficients in the matrix. Here it is 1, here it is 1. But it is being multiplied by yi minus 1, yi plus 1. And you have a right hand side. So you can frame it in the form of ax equal to, you can frame it as in a form of ax equal to b. Is it correct? Yes. So how your a looks like? You have to think, actually I'm writing it here. So check that your a actually looks like this. You can see 1 minus 2 1, that is coming here, 1 minus 2 1. Yes. So this will continue, this will continue. All other elements which I am not writing here is 0. means they don't have a coefficient in them. So till you will get 1, -2, 1 again, 1 here. You can see why I only have a 1 here. That's like the final value, the boundary final value. Okay. But you have it here. You have all those y0, y1, so on till yn. And this guy is equals to, can you say what is it? First initial condition is 0. Y at 0 is 0. Then the next will be minus gh square, right? So whatever you do, minus gh square will be repeating till your end. Till the end you have square. So but at the final you have 50. You have to solve this simultaneous equation. That's it. If you solve, you will get all those y0, yn, and then you can plot it. You have the data. Okay. For this problem, you can approximate y prime 0, which is your answer. Okay. How you will do that? So you will be having like 11 set of equations, I think. Okay, just check it. Y prime of 0 is our interest, but how can you approximate it via a central difference scheme? Yi plus 1 minus yi minus 1 by 2h, right? So here it will be y1 minus, because you know why not, right? So it is 0 minus 1. Tell me this quantity. Y minus 1 actually means our starting point is y0, but what is y minus 1? Y minus 1 is just behind y0. Okay, that is not there, but you can compute it because you know y prime, y1 you know, h you know. You can find y minus 1. We intend to solve it. Since it's a big matrix, you will get around more than 10 by 10 matrix. So it's better to solve using Python. Okay, you can solve using hand also. It will be a bit of trouble. So we'll see the same thing using Python now. This is the same problem we had just now. We are looking at coding like so you can see it's same. N equals to 10 already. H equals to 5 minus 0 by n, which you already have written. Then constructing that matrix A. What I have written Ax equal to B, that is that part of A. It will have only the coefficients stored. So how are we doing it? Storing them in a for loop. Okay. You can set the 0, 0 element and the n cross n element. Those are like the boundary conditions, I mean. Okay. You know that those are already in our equation. Yes. Starting from the second row till n minus 1th row. Okay. Coefficients in. Right. And the matrix I have written it down there is a special kind of matrix because those three, only those, you know, the diagonal of a matrix. Okay. One below the diagonal, one above the diagonal will only have the non-zero elements. Other all will be having 0 elements. That's a special matrix. That has a name to it. That is known as a tri-diagonal matrix. Okay. So generally, once you come to PDEs or set of boundary value problems, it is very natural to encounter this tri-diagonal matrix. And Ax equal to B, if your matrix A is tri-diagonal, then there is a separate way to solve your matrix for X. Okay. And that method is known as a Thomas algorithm. That's one of your project also. You have to implement Thomas algorithm. Why you can't use any Ax equal to B solver? Because your matrix is sparse. It has a lot of zeros. Only those three diagonal, one below, one above, when the diagonal is non-zero. So therefore, like the method can be more efficient than the normal Gauss elimination and all. So therefore, Thomas found a way which is much more computationally faster than your normal Gauss elimination. So therefore, there is another algorithm known as Thomas algorithm, which can solve Ax equal to B, but given that A is your tridiagonal matrix. That is one of your project. So coming back to this, yeah. So I have written down here like using the for loop. Using the for loop, see lecture note. This is matrix, right? See this 1 minus 2 getting shifted by one time in each row. Now 1 will be coming here instead of below minus 2. Minus 2 will be coming below 1. 1 will be coming here. So this 1 minus 2, this array is getting shifted to the right as you progress with more number of rows. So therefore, the same is being done. The same is being done here in the for loop. Learned about like how to do it. You're doing it in a for loop. Okay. You're storing the matrix. I'm printing it here just to be sure that it is actually the matrix I want. And you can see this. Not this line. Ignore this line. Till here. Starting from here till here. You can see we have the diagonal here. Then below the diagonal, one diagonal, we have non-zero quantity. In diagonal, we have non-zero quantity. All others are zero. All others are zero. So this kind of matrix is known as tridiagonal. Tri means above the diagonal, one below the diagonal, having non-zero elements. All other elements are zero. All right. So you have the matrix A now. All right. Then we are solving. You have the matrix A. Now we are initializing the matrix. I just wrote. It's a vector. It's a column vector, right? 0 minus GS square, so on, minus GS square, 50. Yes? Clear? Okay. You have the matrix B. Now you can find the X vector, which is the unknown. How I'm doing it here? I'm doing it not by Thomas algorithm, that's your job. So I'm solving it using the regular package of Python. You can see it here. I'm just providing A and B, matrix A and vector B. So it will solve for you already. So here I'm storing it in Y and then I'm plotting Y, T comma Y. That's it. So now you can understand the code a bit, right? So I have already checked it here. It's the same again. All right. Yeah. Try that one here. And a programming assignment for next class will be, I'll write on the board. Okay, so after you solve the assignment on the board, see it next class. I think, yeah, we can see it next class. Then we can move to partial differential equations. Okay. So it might appear scary a bit in it. I'll try my best to partial differential equations. Okay. So partial differential equations, they usually arise in the study of many branches of applied maths, like mathematics, applied mathematics. Example like fluid dynamics or heat transfer, boundary layer problems, all this. And even like quantum mechanics, electromagnetic theory, all this. Now you can see like there are a lot of quantum data sets, quantum computers. So quantum is a big thing now. Apart from machine learning and deep learning, quantum is another big thing. And only a very few of these equations, like partial differential equations, they usually have some analytical solutions. They don't have analytical solutions to them. And solving most of them, they require more advanced mathematical techniques. As you already know, one of your methods, that is Navier-Stokes problem, is still unsolved. Okay, one of the Millennium Prize problems till now. So of all the numerical methods available for the solutions of PDE, the method of finite differences are more common. So we will see the method of finite differences a lot. Okay. PDE in numerical methods will be, in this course, will be a lot about finite difference. So if you have understood the finite difference of differentiation, then you can easily tackle this. All the things from there will be transferred here. And only things I need you to know is the basic common sense. The basic common sense, okay? So I will just write here how a general linear like partial differential equation looks like. So just focus here, okay? So a linear I will write in a general form. So I'm trying to cover a bit of basic concepts you already know about PDE. I think you already bachelor's, is it? Yes. Up to how much you have covered? It before. So so a linear second order PDE just looks like this. You can use any notation, but I have written in my notes. So like this. A second order term is there, you can appreciate. Y. You have a mixed derivative dou x by dou y plus c of x comma y by 2 plus write it as f. Write it as f. All the terms which are just there, x, it can be a function of x, u, even dou by dou x by dou y, because those terms are not present in your previous terms. Yes. So of the second order linear PDE. Okay. Now such a PDE, how can you, there are different types of PDEs. How can you classify them? So you can actually classify them. So there are three classifications, simple classifications. Elliptic PDE. When you say it is a elliptic PDE, you have C, A, B, C, and F. Okay. Based on these A, B, C, and F, you can actually classify the PDEs. Okay. So if it is an elliptic PDE, if your B square minus 4AC is less than 0. Okay. Parabolic PDE, square minus 4AC is equal to 0. And it is a hyperbolic PDE. Now only one other case is there. B square minus 4AC is greater than 0. Okay. So this is just the classification of PDE. So I'll just ask a question here. Given this PDE, dou to u by dou x2 plus 4 times dou to u by dou x dou y plus 4 times dou to u by dou y2 minus dou u by dou x minus, plus 2 dou u by dou y equals to 0 is a which type of PDE? Okay, so here like in this course we'll try to do elliptic, parabolic, and also like we'll not cover hyperbolic. I think I'm trying to give hyperbolic to maybe as a project. Maybe you can do the hyperbolic. So there are two, let me start with the elliptic equations, okay? So elliptic equations, yes. Elliptic equations are of, there are two famous elliptic equations, okay? Elliptic PDEs. One is known as Laplace equations, okay? Laplace equations. and another is known as the Poisson. Okay, Poisson equations. Laplace is like grad to u equals to 0. Okay, and Poisson is like grad to u is non-zero, that is some f. Okay, these are the just two. We will try to solve only the Laplace here in this equation. However, the method we learn in Laplace can be generalized Poisson equation. Okay. This Laplace equation, which are of this form, del 2u equals to 0, how it looks? Del 2u by del x2, del 2u by del y2 equals to 0. Okay. How this looks? These actually, they come from a physical perspective, like from like maybe steady state equations or electromagnetic equation, electropotential constant. Okay. So next class, like we will try to attack these problems using finite difference. As a hint, you can approximate the second order partial derivative using, but we will make some grids and solve it. Okay. These kind of equations are usually defined on this closed region, as you can see on the figure C. And usually these boundary points, the values are being specified. And we want to know what are the values here inside these. That will be our concern. How we will solve it? We'll try to like make these grids. Okay. And try to solve using the finite difference. What are these values at these grids? The more finer grid you will make, each of these points you can. That's the basic idea. So next class we will look at the how to solve like Laplace equation. Then we'll move to diffusion equation, like heat diffusion. Okay. Hyperbolic can be a wave equation, as you already know. So maybe that can be a project for research scholar. So yeah, with that.